Hello, and welcome to day 4 of energy. All right, so today we're going to be doing two separate things. First off, we're going to be talking about how to deal with uncertainty calculations, and number two, applying them in a lab that seems rather straightforward, but there's more than meets the eye. Okay, why not? I'll just start off with this uncertainty joke. Okay, three statisticians go hunting. When they see a rabbit, the first one shoots, missing it on the left. The second one shoots and misses on the right. The third one shouts, "Yeah, we hit it!" Okay, and that's just a reality. Most measurements are based upon statistics. All right, so there's going to be uncertainties in all of our measurements. So as ridiculous as that story is, you know what? In grade 12, that's a reality. Okay, that uncertainty joke just becomes the reality of finding out where an electron is because you can never see it. You have to go based upon stats. Okay, so let's just start off with regards to how do we deal with uncertainty calculations. All right, every measurement has an error associated with it. So as for addition and subtraction, first off, you add your measurements together. And number two, you add your errors together. I'll leave this part up and I'll leave you a sample question. Some people are wondering, shall we take notes? I think the preference is up to you. If you want to take this note down, by all means, remember that this is available in Google Classroom as well. And we're currently recording, so that's up to you. If there's anything that I find far more of a relevance, it's to practice, right? So you want to practice through these questions. So I think more relevantly is to go through the example, and then you can write down what notes you need to remind yourself on what to do. Because what you have written up above are just the words that explain what to do. That's it. Okay. Okay, so I'll just leave it at that. For those that want to copy the words on top of down, by all means. But just following along with me and then going through practice in your homework, you'll have a better idea of what these rules are talking about. Okay. In fact, before you even answer this question over here, let's just talk about just measurements in general. Okay. You eyeball this length over here plus minus a centimeter. You take another pencil and you're eyeballing its height plus minus another centimeter. When you place them on top of each other, again, this measurement had an error and this measurement had an error. So here's the consequence. If this one is off by a centimeter and this one's off by a centimeter, maybe you measured too short in both cases. So in other words, your final answer is 2 centimeters longer than what it should be. Or let's say that in both these cases, you overestimated both of them by a centimeter. So your final answer should be 2 centimeters shorter than what they should be. And that's what you do with that addition and subtraction, okay? It doesn't matter if you're adding the two values together or if you're subtracting, your errors, unfortunately, will only get worse. So you add the measurements and you add the errors as well. And that's what we're going to do here. 240 plus 212 will give you 452.0, right? When you add these two numbers together, because you're that good at mental arithmetic. Okay, so 452.0 centimeters. Again, with regards to errors, unfortunately, the errors will always get worse. Doesn't matter if you add or subtract. All right, so your error at the end of the day will be 0.1 centimeter plus 0.1 centimeter, which gives you 0.2 centimeters. And that's how you deal with uncertainty calculations in addition to subtraction. What does that sign mean? Plus minus error. Plus minus error. Again, your errors in general will only get worse, all right? You can't just keep on adding things and expecting to get closer and closer to the correct answer, all right? As long as, anytime you add in more factors, you know that your results will become more and more skewed. And that's why whenever you're dealing with any sort of measurements, you want to keep your errors as small as possible in the beginning. Not sure if you guys ever tried doing construction before or building things as a hobby. That's why every piece of lumber that you measure before you build your hobby desk or whatnot, it needs to have as little error as possible. Because the more errors you have in your construction, the more wobbly your desk will be, right? It only gets worse the more off you are for each part. So you want to keep your errors as small as possible, and you know they're going to compound or add on top of each other. Okay? So that's what you deal with addition and subtraction. Here's an addition example, and we'll repeat it again for subtraction. Okay, I hope you guys didn't get the answer of negative, what is it, 3.8 plus minus 0.2. That's the wrong answer. Be careful with the units. Okay, You're not comparing apples with
Oops.
apples right here.
Yeah, I screwed up. I fell for it. I fell for it.
No worries, no worries. That's why
Rip.
I give these questions out. Okay. So how do you deal with something like this? In general, because you know that you're always going to get a cruder answer, always use the larger unit for what you're going to convert into. So in other words, re-represent this in meters. Okay. If you have crude givens, you know your answer is going to be crude at the end. You can't have something that's crude and approximate and have an exact answer at the end of the day. That's not possible. Okay, so we're going to convert everything into meters. So 5 centimeters translates into this, and 0.1 centimeter is plus minus a millimeter. Now we can do our proper arithmetic. Again, we're going to subtract 1.2 by 0.05. So we have 1.05 meters. That's true. Next, with our uncertainties, again, your errors will never get any better. It'll always get worse. So we need to add these two together. You're going to get plus minus 0.101 meter. Oh, I made a mistake. 1.015. Sorry about that. Did I write it down? I probably did. Yes, I did. Okay. All right. So you're going to get 1. Oh my gosh, my mental math is that bad, huh? Oh, it's terrible. Terrible. 1.15 plus minus 0.101. So I was correct the first time round. I double guessed myself. Oopsie daisy. Now here's where the problem lies. Okay, the first one we didn't see it because it looks clean and makes sense. This one over here, there's a problem about stating this. You're telling a reader that at the end of the day, after you're done with your measurements, you think at most you'll be exactly off by 0.101 meter. You're telling the reader that you can be exactly this far off. All right, this is the worst case scenario, exactly down to the millimeter that it could be off by. And that argument doesn't make any sense. All right, if you're off by something, you just know you're off by something. You don't know exactly how off you are by. You know an approximate range, and that's it. And that's why the secondary rule, you can either follow the one up here or just follow the general rule, is that your errors, because they're approximate, they should only be represented by one significant figure. Okay, so really it should just be plus minus 0.1. Another way of seeing it is that this one is estimated to the nearest tenth. This one's estimated to the nearest hundredth. So 3 decimal places versus 1 decimal place. Well, 1 decimal place is less precise, so your final answer should also be 1 decimal place. So that's why your final answer is 1.2 meters plus minus 0.1 meter. Okay, so you can either follow the rules that are listed up here, that's correct, or part 2, which is also valid, is that your errors are always going to be approximate. You can't have an exact error. If you knew you were exactly off by 0.123 millimeters, then why didn't you just add 1.23 millimeters, sorry, 0.123 millimeters to your measurement, or subtract 0.123 millimeters to your measurement just to get the correct answer in the first place? I don't know if that conveyed properly there, all right? In other words, if you know that you're exactly off by this much, okay, the exact off you're off is by this measurement here, whatever it is, why not just add this to your original measurement or subtract from your original measurement, and then you got the original proper answer. Okay, so that's why errors cannot be exact. You don't know how exactly far off you are. You just know the range you're off by. Okay, so I mean, if you want me to clarify, I can just go through, I'll just use this number over here just as a random number. This plus minus 0.1, this just tells you the extreme that you could be off by. In other words, you could have been off by 0.03 centimeters. That could have happened. In other words, your answer could have been as high as 212.003, no, 0.03 centimeters. That could have been your measurement, but because your error was 0.1, you couldn't see that detail. You knew that was roughly closer to a 0 than anything else. Okay, so that's all that plus minus means. It just tells you like this is probably going to be the extreme of what my error is. I mean, if my error is any bigger, then yeah, I would state that my error is probably even larger. So your errors should only be one significant figure. That's the key thing. Okay, errors should only be one sig fig. That is true in all cases. Okay, and you always add errors. Always add your errors. Don't subtract. Errors only get worse. Any questions so far before I advance on to multiplication and division? Now, some might be wondering, well, hey, how come I had 0.1 here and I ended up with 0.1 here? Well, that's the reality whenever you have a crude measurement added and subtracted with a very precise measurement. All right. You will still have a crude measurement at the end. If you remember the first day when we met each other, I talked about a story about me trying to steal something from this office, and while running out, I accidentally stepped on top of a paper clip. All right. And I knew the exact thickness of this paper clip. So by me stepping on this thickness of the paper clip, do I become exactly this much taller when you observe me from far away? If you only guess that I'm roughly around 1.6 meters tall, me stepping on this does not suddenly make me 1.60005 meters tall. It doesn't. I'm still roughly 1.6 meters tall. Okay, that'll be something just to add on to this question here, or the statement here. Okay, so that's the rules for addition and subtraction. Now let's move on to multiplication and division. And here's where things start to get rather weird. All right, you'll still multiply and divide your number as you normally would, but with your errors, you don't just add it right from the beginning. First, you need to convert your error into a percentage error. And yes, there is a formula to convert into a percentage error, and that's what we have right up there. Okay, so your percentage error, you take that by taking your uncertainty and dividing it by your measurement, and that's how you get your percentage error. Often it helps if we have an example. Okay, so again, the 240 and the 212, you will just multiply them as you normally would, but your errors, you need to factor them by adding a percentage error. It's also known as relative uncertainty. If I rewind back, I forgot to mention to you, this type of uncertainty, when it's plus minus 0.1 centimeter or plus minus 0.1 meter or even plus minus 0.001 millimeter. When you talk about it and there's units, that's known as an absolute uncertainty. Okay, so these are absolute uncertainties because it has a unit. Relative uncertainty, which is this slide over here, is anytime that you state it as a percentage, like I have a 10% error. Okay? So that's what we want to do. We want to convert this absolute uncertainty into a relative uncertainty, and this is the formula used to solve for it. Again, what you do is you take the uncertainty of 0.1 centimeters and you divide it by your measurement of 240.0 centimeters. And to convert into a percentage, yeah, you just multiply by 100%. Exactly what we see up here. Okay, so that's all we're going to do. The vertical signs, if you don't recall, it just means absolute value. In other words, we don't care about the minus sign. Just ditch the minus sign. It's irrelevant in our calculations. So you have to show that for every time that you have a relative measurement. Okay, you got to convert it, sorry, an absolute measurement. You need to convert this absolute measurement into its relative measurement. And now let's rewrite the question again. Okay, so it's the same question, but this time around, we've converted it from an absolute uncertainty into a relative uncertainty. And we did that for every single case. This side step you have to do whenever you multiply, divide, or use any form of trig. Okay, so for multiplication, division, and any form of trigonometry. I'm just telling you that's trigonometry, that's part of this rule. Do you have to do that this school year? No, you don't. I'm just telling you that that falls under the same rule if you're curious. Okay, so the first thing we're going to do is we're going to multiply this value here by this value over here. So we take out our trusty calculator. Come on, calculator. What happened? There you go, trusty calculator. So we're going to multiply the 240 by our 212. And that will give us 50880. That's fine. Again, errors only get worse. You're always going to add the percentage error. So you're going to add this 0.04 with this other 0.04. Add them together, and you end up with this larger error over here. Okay, and now what we're going to do next, well, we need to figure out what exactly is this of that. What is 0.08% of 50,000? So we're just going to multiply that in our calculator. We're going to take out our calculator and do 50880, and we're going to multiply it by 0.0. Let me just do this correctly. 0.000889. Remember that this is a percentage over here. So we need to convert into a decimal by dividing by 100. And that's why I had to add an extra 2 extra zeros up here. Okay, so 50,880 times this as a decimal value, not a percentage value, gives us a measurement of 45.23232. Okay, so 50,880 centimeters squared plus minus 45.23232 centimeters squared, or something crazy like that. Yeah. Okay. And this goes back to my previous example I talked about. Can you absolutely know that you're exactly off by this number here? Once again, just going back to that analogy, if you knew you were exactly off by 45.23232 centimeters, why didn't you just add that to your original measurement or just subtract it so that you could get the proper answer in the first place? Okay. Uncertainties, its whole purpose is to say that I have an answer here, but I really don't know if this answer is spot on. So I just want to tell you, just to let you know that my measurements could be off by about this much. And under that argument of about this much, your uncertainties should never show that many significant figures. The general rule is that your uncertainty should only show one significant figure. Some textbooks will say sometimes you can slide with 2. We'll just stick with one convention. We'll just say 1 sig fig. All right, so 45.23232 is the same thing as 50-ish centimeters squared. So your final answer would be 50,880 centimeters squared. You can see that you've rounded coincidentally to the nearest tens, and the uncertainty is also to the nearest tens as well. Okay, and then that would be your correct final answer. 50,880 centimeters squared plus minus 50 centimeters squared. And that's it. I think I have this all PowerPointed out as well. It's the same craziness right there. Okay. I would just get rid of that version there. I don't want to deal with that one. Just deal with that one there. Okay. Yeah, student has a question?
So I just want to clarify. So no matter whether it's up 0.5 or down 0.5, it's supposed to be rounded up by 1 centimeter?
Oh, okay. I don't want to deal with that crazy exceptional rule. Okay, I know there's an exceptional rule which states that if you're exactly at the midpoint, then you should follow suit. It's the one which is that if you are exactly at 45, but you need to round to the nearest tens. Okay, so you need to round to the nearest tens, then yeah, technically that would round to 40. All right, but I don't want to go through that weirdness exceptional rule. Instead, this one over here, you'll notice that you're at 45.2. And because you're at 45.2, you're closer to 50 than you are at 40. That's why I rounded to 50.
So you will always be like 50, 60, 70, like these whole numbers?
It will be just one significant figure. That's the important thing. Okay, this
okay.
should only be one sig fig. That's the most important thing.
Okay, got it. Thank you.
Okay. Yeah, you know what? I should leave this alone, and I'll just delete this part here. But this is always true. Okay. Yes, another student has another question.
Sorry, my connection was buffering. Do you mind going back to the equation and just going back to how you got like the 5,880 centimeters squared?
So this is all recorded, so if you want to watch back there, that's fine. Remember that what's going on over here is that I'm still multiplying. So I'm multiplying 240 and I'm multiplying 212 to get me to 50880. Okay, so I got that 50880 by multiplying those two. And as for errors, I'm just following this rule on top. Always add the percentage error. So we're adding the 0.04 plus another 0.04 to give us a 0.08. Does that clarify your question?
Yeah, thank you.
Okay. All right. So again, everything here is recorded. Are there any other outstanding questions before I stop the recording? Okay, I think everything that needs to be said has been in this recording. So yeah, thank you. For more episodes like this, make sure you like, click, subscribe, and I'll catch you in the next episode. And then how do we end off? I don't know. Some people like to do palm in your face.